on-policy methods like proximal policy optimizations are way below soft actor critique and other offline off-policy methods. But as I said, it's not like it's specific to what the community has used as benchmarks, and my personal point of view on that is that it depends. And in most flow control cases, I have way better results with proximal policy optimization, even on simple ones. Okay, so let's move on. So we'll go on a few technical aspects. Not too much because it would be way too long. So I'll try to unroll the process of how things work, and then we'll move on to the coupling with numerical solvers. Okay, so we just have to introduce a few words now before going further. So you remember, as I said, a step of observation, action, reward is called a transition. Well, if you just take many successive transitions from a starting state to an end state, a terminal state, it's called an episode, okay? Not all episodes in one environment, not all episodes may have the same amount of transitions. You can have different terminal states, and so it can shorten or lengthen the number of transitions in an episode. And just taking the succession of state actions is called a trajectory. It's a bit different, but it's more like a Markovian word for trajectory than episode is more the common word. So a terminal state or termination state is what ends an episode. So it can come from for different reasons. So either you got to the normal end of the episode, like you said, the episode is 200 transitions, and that's it. So it's environment defined. It can be a premature end, like an episode is 200 transitions, but if you get into a particular state, then the episode should end, like you can't recover from that state, or that's an undesirable state we don't want to pursue further. So it's also environment defined. You said that this is a final termination state, or you can have a failure, like your device, your simulation crashes, your experimental device makes something weird that doesn't make sense. You also have to account for that in your agent. Otherwise, your whole learning process is screwed. And so what we call the horizon is the number of steps, number of transitions we have to reach a normal termination of an episode. Okay, so now we go a bit further. We have to define a few other things that are called, so the reward. You remember a reward at time t, we call it small rt. Okay, the small rt that is here, and you remember it represents the quality of the instantaneous quality of the action that was taken given the state we were in. Okay, but if we want to, you have to imagine that in many cases, some actions have immediate outputs, but also long-term outputs. For example, let's say you're driving, and at some point, like you see that there is a traffic jam somewhere. If you say, okay, I'll turn left now, it's a longer path, but maybe I won't have a traffic jam on this path. Then the immediate reward may be a bit lower because you're taking a longer path, but in fact, the long-term reward is you will probably get there sooner than if you had pursued the shortest path. Okay, so in fact, what we look to a lot is the discounted cumulative reward, which is actually a sum from the present instant to the end of the episode of the present reward plus the discounted next reward plus the discounted next reward, etc. And you see that the discount increases. So the multiplicative factor decreases when you go further in time. Okay. Of course, you cannot know this value before you have ended the episode, or at least not easily. Okay. But it represents the impact of an action, present action on future rewards, and we use it a lot. And in fact, that's what we are actually trying to maximize. We are trying to, at a present instant, take actions that will maximize not the immediate reward, the instantaneous reward, but the long-term reward. And the discount factor is, in fact, a user-defined choice. So it's environment defined. Okay. Also, what we call a policy is what maps the state to the actions. So in fact, the agent is mostly holding a policy. It can be done different ways. So we can have deterministic policies, which means that the output of your neural network that defines your policy is actually directly the action, or more often it's stochastic, meaning that your neural network does not directly output actions. It outputs the parameters of a statistic distribution from which you will sample actions. Okay, and the exploration of your environment will be performed thanks to the stochasticity of your agent, your policy. The policy can be explicit, so it's the case for these two, okay, for deterministic and stochastic. So you have actually directly access to what is called to the real policy, or it can be implicit, meaning that you choose your actions based on something else, and the something else implicitly defines the policy. Okay. So I won't go dig too further in that, but DQN is in DQN the policy is implicit. In fact, you have never access to the real policy. You have access to a value function which implicitly defines your policy. And so when the policy is explicit, it is parameterized, and how is it done? It's done with neural networks, in fact. Okay. So let's unroll the learning process, and I added this, like it's what we call policy gradient style, because it corresponds to the type of update we have in on policy methods, so policy gradients. It's not, for example, for DQN things will be a bit different. We will have temporal difference style, but I can present everything in one go. So let's go with that. It's a good way of understanding how it works. So I'm still with my cardboard example, okay? And we start in an initial state, S0. We have the position and velocities and angular position, angular velocity. We provide these observations to the agent, and the agent in a way which is explicit, implicit, stochastic, deterministic, whatever, will provide an action. Okay, we provide this action to the environment. Okay, the environment unrolls a transition, and it ends up in state S1, and it computes reward R0. Okay, which corresponds to taking action A0 in state S0. Be careful; it's just a notation. In many cases, for example, in the Bible of reinforcement learning, which is the Sutton book, this is R1. Okay, this is just a matter of notation. I see that, in my opinion, R0 goes with A0 and S0. That's just a notation. So we ended up in state S1. We provide this state S1 to the agent, gives back action 1, leads us to state S2, and provides us with reward R1. And we do that until we reach the end of the episode, which is any termination state. Okay, this is called episode 0. And just as a side note, if you have a numerical environment, the time granularity is not necessarily the same as your numerical solver. You can have more, usually have more numerical time steps in between two states than the actual action granularity. Okay. So you have enrolled one episode, you enroll another one, as many as necessary until you have enough samples. When you have enough samples, you can update the agents by using the appropriate method. So today it's a bit too short to go through all the details. And the update methods are very different, okay, depending on whether you're using deep networks, policy gradient methods. So I'm just not digging into these details. But it's mostly as it's done as any neural network update. You eventually get a batch of samples. You will shuffle them. You will compute a loss that depends mostly on the algorithm you have, and you will update your neural network, your neural network or networks depending on the method, because most often we have many networks that do different things in the agent, and we'll update them with regular approaches like Adam and stuff like that. Okay, and so you will produce this. So you collect samples, update the agent, collect samples, update the agent, until you get a trained agent, or at least we hope that we get a trained agent. Okay. So how do we monitor that the learning happens? The first one is, the main one is the cumulative reward, so not discounted this time. What we look at is the sum of all the rewards during an episode. So here you have the episodes unrolling. Okay, I didn't mark where the learning states were, but it's like every few episodes. And here you have what we call the score, which is the non-discounted cumulative reward. In this case, it's the carpal case. You see that the maximal score is 200, so we can go any further. And you see that the learning happens pretty fast. Okay. So that's the first thing you will monitor. Okay. But you can monitor many other things, losses. So be careful that the losses have a different meaning in reinforcement learning than in supervised learning. Very different meaning. You can also monitor the entropy in the case where you have a stochastic policy. The entropy will just measure more or less the randomness of your policy. So meaning that the distributions that your agent is outputting, given the states, have a variance that reduces with time, meaning that the agent feels safer and safer about its choices with the training as the training goes. Okay. You can have many different things to monitor. So I'm just limiting myself to these ones, but yeah, you can have other stuff. Just a few words about what could happen poorly, and it's actually one of my preferred sayings that it's very easy to do to make deep reinforcement learning not work. Like it's the easiest thing in the world. For example, you have something that works perfectly here. You have your learning curve that works perfectly. You say, okay, let's just switch from the Adam optimizer to the stochastic gradient descent optimizer, taking everything else, leaving everything else the same. Okay, all other hyperparameters are the same, and you see that it just doesn't work at all. Okay, while you could be expecting that, okay, there are two neural network optimizers, maybe one will perform better than the other, but should work. It doesn't work, okay, because sometimes it's just very sensitive to hyperparameter tuning, and that's a shame. Okay, people are working a lot to design methods that don't depend too much on this. So what could go wrong? Like the environment design could be poorly made, like a selection of observation, the design of the reward, as I said earlier, the agent design, so the network architecture, learning rates, time equality, optimizers, whatever, gradient clipping, or all the things we usually do. And also the sampling cost, like you could be too cheap on the amount of samples you want to provide to your environment. Actually, you must not be too cheap, otherwise, even with CPU in expensive environments, otherwise you would get poor results. So now I'm moving on to what we do, in fact, in the team, like the coupling with computational fluid dynamics. So as I said, we have an in-house deep reinforcement learning library that we have been working on for a few years. We also have our own solvers, and I'm just trying to give a bit of context of why we are doing that, and we are in a good position to actually work on numerical flow control with deep reinforcement learning. We have everything we need. We have all the knowledge, more or less, in the team. So that's why we are mainly focusing on that. So a bit of timeline of what happened in the recent years. So this is extracted from a review I made a few years ago. You see that things started slowly around 2016. There is one paper from 2013 that just went totally unnoticed, but was like borderline deep reinforcement learning, so I didn't include it. So things started slowly in 2016, 2018 with swimming problems like micro swimmers and all. And then the topics expanded a bit to drag reduction, microfluidics, shape optimization, heat transfers and all. Okay, so every dot is a paper, and you see that at when the paper was submitted around the end of 2022, we were we had very few papers in hands, like a few tens. Things that have exploded in 2023, like literally exploded. There has been like the same amount of papers in almost 6 months. So first, I'm really happy that I wrote the review at that time, not later, and also it means that the field is attracting more and more people, and that it has that it testifies of the interest of doing that. Okay, we hope at least. So that's why we are also focusing on that. So if you're interested, these are the two review papers we wrote. The first one, 2021, from a student of the school, and so this one is like very light, let's say, in terms of technical aspects. Okay, it's more just giving a general vision of what was happening at the time. This one so has been published in a journal since, and yeah, this one is much more technical. Like we focused really on many technical aspects. What are people actually doing? What are the hyperparameter choices people make in the community, and comparing them, putting them in large tables to see everything at once. So yeah, this one is a bit more technical than this one. So yeah, when the environment is actually a numerical solver that you interact with, you can have. Sorry.
Hello. Excuse
Hello?
me. Can you hear me?
Yeah.
So very quick question. Do you perhaps have also an archive link for the second paper? Can you share in the chat?
Yes, of course.
Thank you.
Okay. Is archive here? If my connection wants to, of course. Okay. Chat. Yes. Okay. Okay, I think you should receive it now. Is it okay? Okay.
Yeah.
Perfect.
Thanks. Thank you.
No problem. So yeah, when we are coupling with an environment that is actually a numerical solver, you have a few things that must be taken care of that maybe do not happen when you're working on robotics problems, experimental problems, or cheaper, like in the sense of CPU. I mean cheaper environments. Okay, in the sense of CPU time. So yeah, when you running an episode can become excessively expensive in terms of CPU time. You can you want to go for sample efficient methods. Okay, like everything you focus on is sample efficiency because it can be so expensive. And in fact, as I said before, off-policy methods, which are supposed to be sample efficient, at least from my experience, don't deliver to the level where we expect them. Okay, so from my point of view, the exploration, the exploration pattern of these methods are not directly very well suited to flow control, and they're probably tuned for very, very complex control problems, like locomotion is a very complex problem, where a lot of exploration is needed, like a real lot. And in fact, we don't actually most of the time really need a lot of exploration. We need, of course, to explore the environment, the state space, etc. But we need stability, and we need not immediate performance, but we need to have a sort of smoothness in the improvement of the performance, because we don't know how much CPU time we will have. Maybe if the training goes on for 2 days, we don't want to have to spend 1 day having nothing. Okay, which can happen with off-policy methods that can learn just everything at once. And so we want a progressive learning to happen. So it actually, for now, more happens with on-policy methods, although they are less sample efficient. I'm not saying that off-policy methods are worthless for what we do. I'm just saying that maybe they're a bit harder to use, and they don't always fit. Some other thing. So as I said before, what we need to do for learning is collect transitions. So go state, action, reward, and unroll episodes and episodes and episodes. Okay, so in most cases, we can do that in parallel, like unroll set parallel episodes and then gather all the transitions and update with that. But in fact, if you have a CPU, a parallel solver, you can get into problems like, for example, if your environment parallelism is based on MPI, you may not be able to use your solver parallelism if it's also based on MPI. Or if you have a parallel solver, but you have a parallelism in the environment that is based on multiprocessing, for example, so shared memory, you would get into trouble exploiting large cluster architectures with different nodes. And in fact, we ran into that and had to rework everything in order to be able to exploit large computing clusters, because shared memory has some limitations on that. So it's a bit important to know that beforehand. You could also encounter some numerical stability issues, because you never know where the agent will guide you with the actions. Like, for example, if you have, let's say, a transport equation or a Burger's equation that leads to shocks. If you have a forcing term in it for your control, that's something I did recently for a future paper. In fact, if the exploratory pattern of your agent is a bit too violent, in the sense that maybe it will just force in one direction all the time, it could just break your numerical solver, meaning that your numerical solver is stable in the most of the time, but it's not as stable as you thought in the case of disturbances. Okay, that's actually a very important big issue we had, and we had to like adapt a bit. Also, the selection of meaningful observations is a big problem, because you have a lot of redundancy in your numerical simulations. Like if you select information at different probe points in your domain, you're never sure that you're not like overwhelming the agent with redundant observations. And redundancy in observations will mean that the agent will have to work out what is important and what is not during the learning, so during the processing of the observations, and that will lead to a delayed or a slowed down learning. Okay, so it's actually pretty important to work on that and try to be not cheap, but not provide too much observations and select them well. So we are also working on selection mechanisms for that. There has been a few things in the past years in the literature to select meaningful observations, from what is available in the simulation. And as I said before, literature benchmarks are not necessarily the best for this topic. So we are also trying to design a benchmark library, like with environments that are meaningful in terms of simulation and physics, but also acceptably cheap to compute, to run. Okay, that's an ongoing work that should be released before the end of the year. So I'll present a few cases that we have reproduced. Okay, so this one was one of the big ones, meaning that in 2018, 2019, this was the big paper that was issued. And so I don't really know the background in computational mechanics that everyone has, so I'll try to remain very simple. So forgive me for that in one way or the other, depending on what's your background. So this is the 2D flow behind the cylinder. Okay, you have a Poiseuille flow at the inlet, and the Reynolds is 100. And so what you observe behind is the classical von Karman alley. Okay, so we have the flow detaches, reattaches later, and you have what we call a recirculation area behind the cylinder. And the flow exerts a certain drag force on the cylinder. Okay, and this drag force is, if your cylinder was a plane, is what would cost you fuel, for example, to go through. Okay, the higher the drag, the higher you have to push to go through the air. Okay, what you want in a plane is more lift. And so lift would be the force that is exerted in the vertical direction, and the drag is the force exerted in the horizontal direction. So what you would like for a plane, for example, is maximal lift, minimal drag. Okay, and what we would like to do is say, can we add some sort of small forcing that would help the cylinder feel less drag without the forcing costing too much. Okay, so we would like to reduce the drag exerted by the fluid on the cylinder. So how we do that? We have, in fact, two little jets at the top and bottom of the cylinder, and we have only one action, meaning that the total mass flow rate of the jet is 0. We cannot blow or suck the fluid at the same time on both jets. If one is blowing, the other is sucking, and reverse. And these jets are under-actuated, meaning that they cannot modify the flow just by pure momentum. They cannot blow that hard that the flow is totally modified. They have to find a smart way to modify the flow without being too strong. So the actions are actually the jet amplitude in time. So it varies in time, okay, depending on the observations. And the observations are just pressures and velocities gathered on these probes, okay. The reward is a time average drag value penalized by a lift average, a time average lift value, okay. There is a reason for the lift penalization, but let's keep it aside. And so what we are trying to do is reduce the drag exerted on the cylinder in average in time. And so the typical time training of this problem with proximal policy optimization, let's say it's 30 to 50,000 transitions. So it's still a bit. Usually I put the number of episodes it makes, but it's like, if I'm not wrong, 300 episodes or something. If I'm not, it was 80 actions per episode, so yeah, a bit more than 300.
Jonathan, may I ask you something about the reward? Because I see that the reward is a time average direct value penalized by lift, but does it mean also that you can use some penalty in terms of rewards?
Yes, actually, in the reward, you can try to penalize with anything you want. It doesn't. You're just not sure that your agent will understand what you're trying to say through this design, this reward design. Okay, you can try to penalize by saying don't blow too hard. So you could penalize by the amplitude of the jets you use. Here, in fact, you just penalize by the lift, because otherwise the agent is cheating, because the most efficient way to reduce the drag in that case is in fact to blow 100% always on the same side. Okay.
So there's no distinction between the rewards and penalties. So there can be only in one kind of a loss function.
Yes, here there is no differentiation. So it's not a multi-objective way thing, if that's what you mean. Yes. This exists now. It's very recent, but it exists. You have a few papers on that. It's pretty hard to put in place, but it seems very promising.
And does it also apply to the constraints as well?
Yeah, you can actually use multi-objective, it relies on Nash games, and so you can actually have true multi-objective deep reinforcement learning, but it's way more complex to make it work. But it seems to work from the papers that I've read. It seems to work.
Thank you.
So it's fairly recent, but it works.
Thanks.
So yeah, in that case, we just penalize with like the Borman's penalization. So we just have the reward and subtract another term that we want to that corresponds to a behavior that we want to avoid. Okay, so this is a short video. So on top, I think there is no control at all. So we just see the classic von Karman alley, and on the bottom, it starts with no control. At some point, you will see very shortly a few things happening on top and bottom of the cylinder, and then you will see the behavior change behind the cylinder. The actuations are still there, but they are very, very, very small. Okay, so you won't see them on the simulation, but they are actually here. This is the classical. So the control starts, and you see that the recirculation bubble extends and extends, and at some point the flow is almost like around Reynolds 50. So you actually, we barely see the we barely see the detachment at the rear of the recirculation bubble. Okay, so it stabilizes the thing a lot, and you get, if I'm not wrong, you get something like 13% decrease in drag by doing that, and the actuations are very, very small. So that's the history of the drag. Okay, so Cx is the drag. So this is before the control starts, and with no control, you keep just going eternally the same. And with control, you see that the first actuations are actually modifying the flow, and then things decrease slowly until a steady state with like 2.95 something, instead of average value of 321 or 322. So yeah, this is very interesting. And another interesting thing is that the actual training phase only happens on this duration from 0 to 20. So this is what we call an exploitation run. We just try to see what happens when we run the thing eternally. And in fact, while the agent has learned only between 0 and 20, it manages to maintain the flow in the same configuration for quite some time. You see that at the end, new small disturbances happen, but they just remain at the same level for quite some time. Okay. This is a second problem that was also presented by a student of ours a few years ago.
May I ask?
And sorry?
May I ask something about?
I can barely hear you.
I don't know if you're me now better.
I don't
So it
hear
seems
you.
there's a question online.
Yes, I don't hear really well the question actually.
Yeah, but can you hear me better?
I think we can't hear you. Could you maybe put your question in the chat? Is this the one? Can you also elaborate on the?
Okay, on the computational time and training time, yes, I can.
Okay.
Okay, so elaborate on computational time and training time. Computational time, I think the whole, like one episode was something around 3 minutes. I have the figures somewhere, but I'm sorry I didn't put everything on the slides. This was a parallel solver and it was something like 3 minutes or so per episode, with a pretty refined mesh, like to be very sharp. And in fact, we used parallel collections of transitions. So the training time, I would say it depends on what you're actually doing. It depends a lot on your solver, because if you have a crappy solver, it can take forever. And it depends on if your solver is parallel, if you're also using parallel collection of samples. The initial, if I remember well, so I'm just speaking about this paper, not what I did here. So in the end, my training for that was something like 3 hours, 4 hours, if I remember well, for the whole thing. It was, and I had 50,000 transitions. If I remember well, the original paper was no parallel transition collection, and it was using Phoenix as a numerical solver, so pretty slow. I think it was 24 hours a run, while I was having 24 hours for 5-6 runs. And in the end, I think a few people worked out the things in under 10 minutes by using massive parallel collection of transitions plus a very fast GPU lattice Boltzmann solver. So it depends. I mean, you can't have a definitive answer on that. But it's a good question, because it makes a lot of difference. Like 24 hours, 10 minutes. Yeah, of course, there's something there's something to discuss here. And so an efficient CFD solver is the first step. And parallel transition collection is like a must-have. If you don't have that, it's very likely that you will never get anything out of it. And this is a very simple case, like 50,000 transitions. Where am I? Oh, 50,000 transitions. It's nothing. If you remember the locomotion problems, it was 5 million transitions. So it could be much worse. And suppose that we had a 3D problem with 100 million unknowns in the CFD problem. You have to run it at least on 64 cores, and you have to parallel transition with like 10 to 20 parallel environments. You have like, in fact, the problem is not much if you have a good PPO implementation. It's like, are you able to interface everything at once? So you can use a large cluster and perform well on all the parallel sites. So it's very important, in fact. Okay, have I answered the question?
Yeah, we do have a question here in the room.
Okay.
Thank you. So 2 quick questions. The first one, what is in practice a transition? Is it running a CFD simulation until the von Karman, the unsteadiness has more or less stabilized, or is it shorter than that?
So a transition is one state action reward. So it would be just collecting the observations, providing them to the agent, getting an action from the agent, providing the action to the environment, running the environment for a certain amount of numerical time steps until you reach the next step, and that's it. So no, transition is very short, actually. Transition is like, in that case, one episode, so running one full thing from the starting state to the end of the episode was 80 transitions.
Okay, thank you.
There's another, sorry to
Yeah,
interrupt
no problem.
again.
Excuse me, if I am well understood, I think that we can use reinforced learning to optimize the problem, and this one was like an optimization problem. Yes?
No, this one is a control. It depends what you call an optimization and control problem.
I mean that you want to reduce the drag, you have them, yes?
Mm-hmm.
And you want to find the best shape, no?
No, here we don't modify the shape. We have on the top and bottom of the cylinder, we have jets that are blowing or sucking the fluid very slightly.
Okay. Okay.
And the strength of this actuation is dependent on the observations of the environment. Okay, so it's active learning, it's active control. It's an active control problem. It's not an optimization problem. So what we are looking at is a control law that transforms observations of the environment on these probes to a control value that actually varies in time then.
Okay, but we can use this algorithm for optimization if we define the reward as the minimum of a function. Yes.
Yes.
If we have in minimization, we have a cost function. We can have the value of cost function or the reverse of it as a reward. Is it possible?
So yes, it has been done. Actually, we have done that. It will be later in the presentation.
Okay. so it will be described later. But my main question was that is it possible to have, for example, an autoencoder for as environment? I mean that we have reduced the model using an autoencoder. Then we use this model, this reduced model, to make a decision, to to make a decision.
Yes, you could do that the same as you could do it for any optimization problem.
Yeah,
You just have to be certain that your reduced order model is complete and accurate enough to deliver where the problem is. What you have to think about is that probably the control will drag your system in places that it hasn't been before. So if you want to be certain that your reduced order model is able to accurately answer when you're trying to control your system, it means that you have to have trained your reduced order model on cases where you already had the solution.
In fact, what I was thinking about it exactly. Imagine that we have a reduced model, but still very large, obtained by autoencoder. Now I want to reinforced learning algorithm to decide whether it is, let's say, find the smallest possible reduced model for a specific problem. We already has reduced it. We transfer it to a state space, but to a large one. And can we decide that based on some parameters, based on the reward, that what is now the minimum one, the minimum possible one for a specific force, for example, a specific condition?
I'm not sure I understand exactly what you want to do. You would like to change the size of the autoencoder dynamic?
Yeah. For we have reduced the model generally, but then we want to decide the size of the model for a specific problem, for a specific set of data, for a specific set of forces, not changing the geometry.
That means that you would have every transition would need you to retrain the full autoencoder. Is that correct? Is it true? Like, yeah, and that would be like I think it would be like amazingly expensive, but maybe yes. I can say no because I'm not certain about that. I have never thought of that this way, but if you have to retrain your autoencoder every transition, like, yeah, it could take a while.
Okay, thank you.
No problem. If you want to discuss more, you can reach me by email if that's needed.
So I guess we are good with questions for the moment. So
okay, perfect. If at some point you don't hear me anymore, it's probably because my ear things are low on battery, so I will switch to my laptop microphone. But if there is a whole when you don't hear me at some point, it's because of that. Okay, so now let's move on to another problem that was performed a few years ago. So it's the I call it the Shkadov problem. So it's actually because the equations of this problem were designed by Shkadov. It's a sort of Korteweg-de Vries equation, so shallow water equations with additional terms that correspond to ripples that would be created on a thin fluid film that would go down on a sloped surface. Okay, so you imagine that you have a faucet that is dripping water on a sloped surface, and if you let it flow long enough, eventually you will get some ripples, and these ripples will, with time, these ripples will actually develop very interesting instabilities that are called solitones, and that have different celerities, celerities that are different from the rest of the other ripples. So it's a pretty interesting problems in terms of physics. You need a decent TBD scheme to process that, but it's 1D, so it's fairly it's pretty fair in terms of CPU time. And so the idea is that, can we put some jets in some places in order to control these ripples, like kill the ripples in a certain area? Okay. This is a stochastic problem because environment, because in fact the noise generated here ends up being the ripples here. Like it's an exponential instability growth, and so running the environment twice never gives you exactly the same answers. Okay, so we position some jets in the domain, and we try to damp the instabilities dynamically. Okay, based on observations. The typical training time would be 200,000 transitions for 5 jets. So you see that the action dimension has increased, because in this case we had only 1 action. Now we have 5. I have run this one until 20 jets, but you could imagine 100 jets, and it was actually in the original paper, it was actually to we used a translational invariance trick to design n1D problems from an n-dimensional problem, and it worked pretty well. Okay, so in this case, I didn't use the trick, and so this is an example. So in the beginning, you have no control, and at some point the jets just start acting. Okay, and you see that in the vicinity of the jets, until a certain point, we can damp the instabilities pretty well. And as there is no more control later, the unstable behavior of the flow kicks back in, as you again have instabilities developing. That's a very interesting problem. It's fairly cheap to run, and it gives a good approach to high dimensional action environments. Because you can just say, okay, let's go to 20, 100, whatever. Okay, and it was actually used. I recently issued a paper where I used this environment to develop. As I said, parallel collection environment is very important, and I actually developed a way to extend the capacities of environment parallelism for on-policy methods, because we use mostly on-policy methods, and on-policy methods have some limitations on what you can do on parallel collection. And so, in fact, you can see that we can go from, for the training, we can go from let's say 1 hour and 15, a bit more than 15 minutes, down to 3 minutes, 3-4 minutes, with the same, almost the same performance level. So this is a node curve, but yeah, the performance is identical. So that was pretty helpful, and it illustrates how important it is to use parallel environments, and to be able to, as CFD users, it's very important to be able to use parallel clusters. Okay. So these were 2 examples. I didn't put more because we could go on and on and on. So these were 2 I did recently. Now I can move on to the very quickly to the optimization parts. So it's very like a digression from what we were talking about until now. It's just a presentation of what we did when we thought, can we use deep reinforcement learning to perform optimization instead of control? Okay, so we are moving on from active control problem to just optimization. which optimization is just seeking a steady set of parameters that optimize a cost function. Okay. So the idea was the following: can we use DRL tools to have an optimization methods where the output of the actions, like the output of the policy, would be the actions that represent the optimal set of parameters. The action don't depend on state, okay? Because in optimization, you're looking for a constant set of optimal parameters, not a control law that depends on input parameters. And an episode would consist just in a single step to trying to find the optimal actions. Okay.
Sorry.
And of course, yes.
Pardon, a quick question. If this is a stateless problem, why don't, or at least the action doesn't depend on the state, why don't you use bandits instead than reinforcement learning?
That's a good question. In fact, we were looking for more flexibility in the ingredients. And we also look at non-stochastic environments. But it's still a question that people ask when we talk about that. And the last answer was I was actually not an expert in bandits at the time, and I had other ideas. In fact, you will see that we needed some flexibility to add ingredients to speed up the optimization process. And these ingredients are actually, we need a policy with a stochastic, how do you say that? Like we needed a statistic distribution instead of what the bandits can provide. And you will see why. But it's actually a very good question, and maybe we could have also done something similar with bandits. So in fact, what we did very naively was say, okay, it depends on it's state independent. Let's just put a constant state in input and see what happens. And we reduced what we call an episode was reduced to just one transition, in fact. Okay.
Okay, thanks.
So,
I mean, sorry, thanks for the answer. I mean, there are also, I mean, stochastic version of bandits, but okay, I get your point. DRL was more flexible for this kind of problem.
It was more suited for us, and my knowledge of bandits was also very limited. So we just gave it a try, and you will see that it works very nicely. And in fact, what the flexibility we wanted was to say we want to perform the optimization. So we want a policy that will output the parameters of the statistic distribution, but we want to use a multivariate normal distribution with a full covariance matrix. And why did we want to do that? Because in fact, a very standard method in optimization, if you're looking at this method, it's called CMAES, and it's covariance matrix adaptation evolution strategy. And it's an evolution strategy, so it's a subset of methods from evolutionary methods. And it evolves the same kind of things, meaning a multivariate normal distribution with full covariance matrix, and it's very efficient like that. And I wanted to say, let's try to do that, but instead of having a fixed set of rules of update of this distribution, we just leave the network to do the updates the way he wants. Okay, we don't really. Because CMAES is like the definition of heuristics. It's CMAES, okay? It's just a set of rules that seem to be out of nowhere, but works insanely great. And it's just fixed, like you do always the same updates from your new data. And I wanted to say, okay, maybe these updates are good, but maybe we can do very good updates just by deferring the generation of the new distribution on the on a larger problem, which would be updating the parameters of a neural network. So you're just saying, instead of updating, let's say, n parameters of your current matrix, you will be updating a larger number of parameters that will be these of your neural network with ADAM, and these would lead to improvements like using aliasing. So you're just saying that if you try to deport the optimization problem on that of the neural network instead of on that of the final product, which is the current matrix, you will get better results. And in fact, that's actually what happens. So my constant input is just provided to 3 different networks that will output the parameters of my. Do you hear me? Do you still hear me?
Yes, we can hear you.
Okay. Okay. I think I'll just change from my ear things to my regular microphone. Otherwise, I'll be having a problem very soon. Just give me a second. Do you hear me now?
Still, yes. A bit from far away, but yes.
Okay. Sorry about that. Do you hear me?
Yes, we hear you. Can you hear us?
Yeah, perfect. Sorry about that. Okay, so we have 3 different networks to perform to produce the ingredients of the full covariance matrix and normal distribution, and we input constant states, obtain the ingredients from the covariance matrix, and you will see how it goes later. Okay. Just to remember that you can have different type of covariance matrix. You can have either isotropic covariance matrix. So when you sample, when you sample from it, you get in 2D you will get a disk. Okay, with isotropic, it's isotropic in all directions. You can have a diagonal one. So you can have elongations or compressions in either along the axis, so here horizontal or vertical axis, and you can have a full covariance matrix with correlations, and then you can extend the sampling in any direction. And you will see that how this is a very important ingredient, because elongating in a proper direction speeds up the optimization process a lot. Okay, so in fact, what's happening is that at every step, I'm not sure. Yeah, okay. I'll go to this one directly. It will be better. So what we do is that we input the constant states to the policy. The policy will generate the multivariate normal distribution. It will eventually generate actions. Okay, we will sample from it, from these distributions, and we will get actions in. I always generate actions in -1, to the power of the whatever we want, the dimension of the problem. Then you can map these actions to the physical actions. You compute the costs, okay, and from the cost you can form a reward and go back to it, okay. And in fact, what we do is that we follow the same thing as for reinforcement learning. We generate a certain amount of actions, okay, like whatever amount, and we generate we compute the cost for each of these actions, and we form a buffer updates, and we update the policy with that. The idea being that you want to limit the amount of actions you generate in order to be able to limit the computational cost of your problem. Like, you don't want to sample too much from your CFD problem, okay?
So in fact, here what we call every sample action is an individual in the sense of evolutionary methods, and all individuals belonging to the generated with one policy are called a generation. Okay, and what we do is that we try to reuse the previous data from the previous generations with a discount on the previous the importance of these previous samples. Okay, so in order to form the new covariance matrix of the next generation, we use what we sampled at the current time plus the previous generations, but with discounted importance. Okay, and doing that, we managed to generate a buffer that is large enough to provide a meaningful batch update for the policy. Okay, and as this policy generates multivariate normal law with full covariance matrix, we are able to elongate the direction of research in the direction of the steepest descent. Okay, and this speeds up the learning, the optimization a lot. So I will show you examples later. And we have used that in different cases, but also other people have now started using it. So we were pretty happy about that. It's very recent. So people have done some shape optimization with it. We had done some shape optimization at the very beginning, but the performance was of the method itself was slower than it is now. And yeah, people have done a few things with our method, so we were pretty happy about that. And they have investigated possible improvements of it, so it's pretty nice. So just a few examples of what's happening. So this is a simple parabola function. Okay, we just want to find the minimum of the function, which is trivial. And so what you will see is on the left plot, you will see that each yellow dot is a sample from the current generation, and each cross is previous samples, okay, from previous generations. And so we sample a few actions, compute the cost, so just compute actually here the value of the parabola function. We estimate a gradient for the update of our policy, okay, and we update the policy and we iterate again, sample new things. On the right, you see all the sample points. And so this is how it unrolls, and you will find the minimum pretty fast. So it's just parabola function. You could do the comment is very similar to what I did previously with CardPoll. You would get the minimum with a Newton descent much faster than that. But in fact, what we are doing here is gradient-free optimization. Like, we are interested in cases where we would never get the gradient of our cost function. Of course, it's more expensive for simple cases, but in fact, it's more interesting for us to perform GRL against adjoint methods. We are also more interested in gradient-free optimization methods than in gradient-based optimization methods. So this is the simplest case, and you see that we compare favorably with CMAES, which was a nice result for us, like designing a method that was comparable with state-of-the-art of the evolutionary strategies method was a nice achievement for us. We also compare like the regular evolutionary strategy with a previous version of the method that was not using the covariance matrix stuff, and it was yeah, also similar. And we also achieved good results on classical textbook problems that in fact make a lot of use of the covariance matrix adaptation. And so for those who don't know this function, it's the Rosenberg function. And it has a it's not very easy to see, but it has a very narrow valley here from 0, 0 to 1, 1. Okay, the minimum is in 1, 1. And the valley is so narrow that if you use regular isotropic evolutionary strategies or research in general, you will require tens of thousands of steps to get to the minimum, because the valley is so narrow that you're stuck with the narrowness of the valley and you only progress very little at each step. While if you can extend in the direction of descent with covariance matrix adaptation, then you can get very fast results. This is the same kind of stuff. What happens? The algorithm finds the entrance of the valley, okay, and then starts moving up, moving down in this case, and pretty fast goes to 1, 1. Okay, so it also compares favorably with CMAS. And then the method, the agent will converge around the optimum point. So yeah, in this case, similar to previously, like you see the difference between covariance matrix adaptation methods and isotropic methods that will never get there. Okay. This was also another example where we try to design a control law for the Lorentz attractor. So in fact, the Lorentz attractor case was proposed for control in the context of deep reinforcement learning, so with actual active control. But I would just try to design something that would be a handmade control law with the optimization of the different parameters. So here 4 parameters. The goal of the reward was to try to keep the attractor always in the negative X quadrants. Okay, and interestingly, it worked pretty well. So it was a nice illustration. This one is more like an illustration than anything else. So at the beginning, it rolls normally, and you will see that at some point something will happen. Or is it the regular one? No, this is the regular one without. So this is the one without control. Sorry about that. So the control one must be on the next slide. So this is the regular Lorentz attractor, and yeah, trying to maximize what's happening when we to maximize the time spent in the negative X area. So it starts similar, and you will see something at some point. Yeah, you have a big maximum, and then it just locks around the left stable point and just stay there forever. So it was a nice optimization case with a bit of visuals. So it was just an illustration. So this is the kind of curve we obtain, and you see that it converges very fast. So 20 generations, and you have to count like for 4 parameters, we have 6 samples per generation. So it was 120 evaluations. If you use parallel collection in the same case, you get that kind of results in no time. Okay, because Lorentz is quite cheap to evolve in time, so it was pretty fast. There were also in the team some other more industrial-oriented cases. So the idea here was to cool a workpiece that was getting out of an industrial oven. So it's just this square in the middle, and we have 3 inlets, okay, of cool air and 2 outlets. And the idea is that we try to position the inlets so that we get the best cooling possible. And best cooling possible is that we try to avoid high temperature gradients in the workpiece, because during the cooling process, if you have too high temperature gradients, you could get micro cracks inside your workpiece, and in the end the thing is doomed at the end to be thrown away, because it won't match the quality requirements for an industrial process workpiece. So that was also performed in the team. And so this is just a video of all the different sampled cases. So it loops actually. So at some point it will loop. It will start again. And I just don't really remember when it stops. And in fact, the idea was to generate the cooling should be made by generating a recirculation area around the piece and not blowing directly on it. So this is why the optimizer tries to join the two inlets here, because that's the optimal case. Okay, and it starts again. Okay. This was a bit longer, and in fact the computation was much more expensive than the Lorentz case, of course. But we got nice results on that. And so now I will just, almost in time, I will jump to some conclusions on deep reinforcement learning. So as you saw, it has some potential to discover interesting control laws, and also to perform optimization if you tune it a bit. And the performance of the algorithms has improved a lot in the recent years. Now we are, as I said, in the applicative decade. So we are trying to transform let's say the DRL algorithms as interesting beasts for control to actual controllers that could be used in the real life, in industrial contexts, and so on. You saw that environment design can be very hard to achieve, because you have a trillion ways to do one thing, and not always will work. Like mostly you will have a few ways to make it work, and all the other options are doomed to fail. And also you have a bit of hyperparameters tuning to do. It depends on the method you use, what you select, etc. And of course, in our case, the control is hard for CPU expensive environments. So we are working a lot on this aspect. So at the moment we have we are three to work on this in the team, and both on the parallel side, state representation learning, etc. And so the activity is progressing, and as you saw in the different reviews I presented, this topic has a lot of attractivity at the moment. So many people are turning towards deep reinforcement learning for flow control. Okay, so I think that's all for me. If you have any questions, I would be glad to answer.
First of all, thanks very much.
You're welcome, no problem.
Are there any questions here in the room or in the chat? No questions. Everything crystal clear. So I think, yeah, then we can thank you. And Stephanie, do you want to say a few words to close it?
Okay.
You opened it.
Well, I started so I can end. So it was really a pleasure to be able to organize this. Thank you again to all of the speakers that were here. I think we saw a lot of different ways how machine learning and AI can be used in engineering design, and I hope that you got a lot of ideas to bring home with you. Thank you for being here in this room, basically in the same number as you were on Monday. Also, the same holds more or less for the online crowd, I think. So this makes you really a great audience, I think. So I was happy to have all of you here. Thank you also for sticking with us through the technical problems that occurred from time to time. I hope you enjoyed Udine, and I hope you will come back for another TISM course at some point. I hope we did not ruin it for you. You will, from the Secretariat, you will receive a certificate of participation via email. So both on-site participants and also online participants. And there will also be a survey where you can give some feedback on what you liked, what you disliked, and what could be improved maybe. And yeah, other than that, have a great trip back home and maybe see you in some other context.